But what I want you to point out are some features that become more apparent once you make this comparison of the rotation transformation with the Lorentz transformation. It's something called invariant. So when you hear the word invariant, what do you think that means? Doesn't change, right? That's what it sounds like, right? Variant with the in. So like a flammable and inflammable, it doesn't, sorry, that's wrong. But with the variant and invariant, it sounds like, it doesn't change. Yeah, that's what it is. So with the rotation transformation, there's an invariant that you already actually know about, that no one's told you that this is an invariant of the transformation. Like, imagine this. So when you have some stuff defined using this coordinate axis, and when you rotate your coordinate axis, what doesn't change?
The volume.
You could talk about volume. I'd like to keep it one-dimensional if possible. By one-dimensional, I mean, so this point here, I can represent it with a vector. Instead of being a point on the coordinate axis, I can represent this point as an arrow, a vector. This can be my r, right? And when you rotate your coordinate axis, so what this vector is, I guess its underlying physical nature doesn't change. But if you are looking at, for example, the coordinates of this vector, if you are trying to represent this as x component and y component, these components change, right? That's what you see here. So what property of this vector can you bring up that will not change as you change the coordinate axis? Someone else. The magnitude, right? Yeah. So that's what you know as a rotational invariant. It's a quantity that doesn't change. And so in terms of, so Kevin, in terms of vector notation, so when you have the vector, so we have this so far, let me write it down this way. So with this transformation, the magnitude of R doesn't change under rotation. How would you express the magnitude of R in the vector notation? If you're just writing down letters, it would be, magnitude of R, that's R, without the vector symbol on top. But how do you calculate that? So Kevin, how do you calculate that? So you have a vector, you are given the components, right? Okay, how do you calculate its magnitude? Let's say in terms of the components. Function? Okay, so you take the components, and let me do it in the order that I like to. You take the component, square them, add them together, and then take the square root, right? Pythagorean theorem. So you could write the magnitude that way. Let me actually do a bit of an odd thing. Instead of writing it as a component squared, I'm going to write it as component multiplied to itself, plus ry times ry. Does this way of writing it remind you of anything? Yeah, dot product. So when you write it this way, you are still referring to the component, which to write down the components, you need the axis. So in physics, we like to write down expressions in a way it's axis independent. So I can say this magnitude is the vector dot product with itself square rooted. Or let me actually make this simple for myself. Let's not bother with the square root. What I'm going to say is if r doesn't change, r squared also doesn't change. And so this is what you might call rotational invariant. It's a quantity that doesn't change when you do rotation. In fact, we have a word for that. While I'm giving you all the vocabulary, let me give you the one last vocabulary that you have already heard. This is what we call scalar. We call scalar scalar because it doesn't change under rotation. It has no sense of direction. In fact, the only thing rotation changes is the direction. Before, if this was described by this angle phi, then after rotation of axis, the new angle with respect to x prime is different, right? So that's the only thing that changes when you rotate anything. So, so in this two-dimensional geometry, this is a quantity that doesn't change. Now, what I want to do is talk about not a rotational invariant, but Lorentz invariant. So, but I needed to go over this so that you have some sense of what we are trying to model after. So this is a two-dimensional geometry, something you have already great intuition for. So maybe you are not writing this down now. You are not used to writing this down, but this is just a different notation, different way of writing down something that you already know. Now what I'd like to go over is something that you don't already know, that when we are talking about Lorentz transformation, there is a way to write down these quantities, these combination, these coordinates. There's a way to combine them, ct prime, x prime, y, so prime, g prime, in a way that when you do Lorentz transformation, the particular combination of numbers don't change. Now, so, since I'm drawing the comparison, let's see if I can, do the exact same thing I did there, and let's see if that'll work. So let me just do this as a guess. So we are trying to search for what would be a Lorentz invariant, what would not change under Lorentz transformation. So Lorentz invariant. Well, so I guess then following what I see there. So to simplify it, I'm just not going to talk about y prime and g prime. I'm just going to talk about these two coordinates, ct prime and x prime. So if I am following that, I would maybe guess this quantity, ct squared plus x squared invariant. That would be the question. Just as a guess. It's going to be a wrong guess. But we can actually check it. How would you check this guess? Units are going to be correct, but the dimensional analysis only tells you if it's absurdly wrong. If it's reasonably wrong, then you wouldn't be able to tell from units. So this is what something being invariant means. I can actually prove it here with just a mathematical algebraic manipulation. So I wrote this down with the x coordinate, the unprimed coordinates, right? Let me rewrite this using the primed coordinates. Or let me actually do it the other way. It's easier this way. So let's pretend that the r prime was written with this primed coordinates. Now, for each one of the primed coordinates, I know how to rewrite it in terms of the unprimed coordinates, right? And if this is truly an invariant, this should be equal to square root of rx squared plus ry squared. Whether I write down this particular combination of coordinates in the primed coordinates or unprimed coordinates, I should get the same expression. Let's see if it works out that way. Let me, it's a quick algebra, so let me write it down. So say that this is equal to, all right, I'm just going to plug those in. So let me not bother with the square root. I'll just, yeah, so, well, here's the square root, and I'm not going to bother with that anymore. So Rx prime squared. So that would be this whole thing squared. Rx cosine theta plus Ry sine theta squared, yeah, plus the Ry prime squared. So it'd be this thing squared. Let me write it this way. Minus Rx sine theta plus Ry cosine theta squared. Okay? It looks a bit complicated. Right now, it's not entirely clear if I will get what I was hoping for. Let's write it out and see. So, all right, let me expand this out so that Rx, this thing squared, Rx squared, cosine squared theta, the cross term, there's two of them, plus 2 Rx Ry, sine theta, cosine theta. There's this term squared, so plus Ry squared, sine squared theta. Okay? So that's this one term. Let me do the second term just below that to see how it works out. This is equal to first term squared, so the minus goes away. Rx squared cosine squared theta. Cross term, this time it's minus Rx sine theta. So let me write that down.
Sine theta? Sine squared theta? For Rx? Rx squared sine?
Oh, thank you, yeah. Squared sine, yeah. Sine squared theta. Thank you. Okay. The cross term is minus 2 Rx Ry sine theta cosine theta plus this thing squared, so plus Ry squared cosine squared theta. Okay. Now imagine adding them together. In adding them, you will find that they simplify a lot. The cross term, which is ugly and I don't want it, they cancel out. They are the same with just the difference in sign. So, all right, so I still have these 4 terms. Let me collect like terms. Rx squared terms together, Ry squared terms together. Then you end up with Rx squared times cosine squared theta plus sine squared theta plus Ry squared, the same thing. Cosine squared theta plus sine squared theta. What are these each equal to? 1, yeah. So that's a trig identity that hopefully everyone knows. So this is 1, this is 1. So we get what we are hoping for. This thing, Rx prime squared plus Ry prime squared is equal to Rx squared plus Ry squared. So it's a somewhat tedious calculation. I was kind of rushing through it, but you can do that calculation here to see if this is invariant. And yeah, let me just quickly go through it. I think I don't have, so I guess I'm going to have to cut out some examples, or I'll cover some of this on Tuesday maybe. But let me go through this calculation here. So let me change this to the primed ones because I already have the transformation to rewrite primed ones in terms of the unprimed ones. So let me just do that calculation and see if we get what we might hope for. And I'm telling you ahead of time that we want, but the expression we get will give us some idea on what to do so that it'll actually work out. So, all right. So let me do them one at a time. So this is going to be equal to this whole thing squared. So it'll be gamma squared times ct minus beta x squared. And let me expand this out. So expanding it out, you get gamma squared ct squared. And the cross terms, so it'll be minus 2 gamma squared, and then these two, ct times beta x, and then gamma squared times this. So plus gamma squared beta squared x squared. That's the first term. Let me do the second term. The second term is here. So gamma squared times x minus beta ct squared. That's equal to, I'm expanding out the exact same way I did this one. So gamma squared times, I probably should swap the orders. Yeah, let me write down this term squared first. So it's a gamma squared times this thing squared, so plus beta squared, let me write it this way, beta squared ct squared. Good. The cross term, so it's minus 2 gamma squared times b. So it'll be, let me do it in the same order like this. So ct times beta times x. They're all in there in the cross term. And the final, it's gamma squared times x squared. So plus gamma squared times x squared. And when you look at these two expressions, you see that what I mean, that this is not the right combination. Because when you imagine adding them, you don't get what you would be hoping for. The cross terms don't cancel for 1, right? And when you collect the like terms here, you get, so factor out the ct squared, you get gamma squared plus gamma squared beta squared. Is this equal to 1? Yeah, so if you remember that gamma is equal to it's equal to 1 over square root of 1 minus beta squared, it's easier to see. Because when you write it all out, this is what it looks like. You have gamma squared, so factor out gamma squared. You end up with 1 plus beta squared. So you have 1 plus beta squared divided by this thing. So 1 minus beta squared. Well, that's not equal to 1, right? So what would you change? But I feel like I'm pretty close, because when you imagine doing the factorization, what you end up with here, it's the same thing what you end up with here after you factor out x squared. And the cross terms are at least related to each other. They're not canceling, but they are same term. So I feel like this is close. I just need to make one minor modification to actually find the combination of quantities that's invariant under Lorentz transformation. So let's do it one at a time. Let's say I want you to fix the cross terms. I want them to cancel out when I add them. What would you do? What would you change here so that the cross terms would cancel out instead of add together?
Change the symbol to minus.
Yeah, I mean, that's the easy thing to do, right? Change this to minus. Then instead of adding, if I'm subtracting instead of adding, then they will cancel out. Now, what I'm hoping is that this is the same change I need to make this work. Let's see if it does. So, all right, so I'm subtracting instead of adding. So it's this minus this. So that means after I factor out gamma squared, this is 1 minus beta squared. Oh, that will cancel out, and I will end up with 1 that way. All right, so 1, 2 terms out of the way. It has to work for this too. Let's see if it works for that last term. So this last term, what it'll look like is gamma. Let me factor out x squared times gamma squared beta squared minus gamma squared. Well, this is just this thing multiplied by -1. So this is going to end up being equal to minus x squared. Are we okay with that? You should be, because what that's saying is that this is equal to, well, let's add it up. It's saying it's equal to, ct squared, no cross terms, and then minus x squared. Well, that is what I was looking for. Same minus. Okay. So this is the Lorentz invariant. This is what counts as length in the context of Lorentz transformation. And there are actually many more examples of Lorentz invariant where I wanted to bring up at least two more. One involving energy and momentum, and there was one more involving wave number. But let's pick up from this next Tuesday. And we will wrap up special relativity next Tuesday. And by the time I will have all this written up as lecture notes that you can also read instead of listening to, and we'll take it from there. Sorry, this was way more than I could do in 1 hour.